Alright class, today we're studying section 3.2. We are going to be able to solve equations involving fractions. We're going to be dealing with linear equations, or equations have one solution, is probably more a specific way of saying it. When we think of linear equations, we often think of a situation like this, where we subtract 1 and end up with 3x equals 9, and divide by 3, so x equals 3. Our linear equations are going to be more complicated than this. They are often going to involve fractions. Whenever we're dealing with the fractions, there are several ways to approach it. We could get common denominators and multiply to get rid of them. We could do a lot of things, but what I prefer to do is to think about what my common denominator would be. The common denominator between 3, 4, and 2 over 1. So 3, 4, and 1 would have to be 12. Now, since this is an equation, this only works with equations, so I have an equal sign. I can multiply everything in this equation by 12 over 1. By doing so, what happens is I will make the fractions disappear. 12 divided by 3 is 4. 36 divided by 4 is 9. Equals 24. And 9 plus 4 is 13. Combine the like terms. Divide both sides by 13. So x has to equal 24/13. I'll also be approached with situations where I have fractions equal to fractions. You probably remember this from your previous math classes, but when you're approached with this situation, you want to do what is known as coarse multiplying. This only applies if you have one fraction equal to another fraction. I had to use the distributive property to get rid of the parentheses. Now I'll combine like this. I'm going to subtract 9x from both sides to get 3x plus 15 equals 9. And I'll subtract 15 from both sides and end up with 3x equals -6. And my answer ends up being x equals -6. So, whenever we end up in a situation where we have x's in the denominator, like the previous example, we need to be aware of extraneous solutions. An extraneous solution is a solution that we end up with, like we do all of our solving and we end up with x equals 3. But when I plug that back into the equation to verify, it ends up not creating a true statement. So let's go back and look at this example again. My solution is x equals -2. So if I plug -2 in for x, if this solution is a valid solution, then when I simplify this statement, I should end up with a true statement. So -2 plus 1 is -1. 3 divided by -1 is -3. 4 times -2 is -8, plus 5 is -3, and 9 divided by -3 is -3. Since -3 equals -3, it is a true statement. So x equals -2 would be a valid solution. But sometimes we end up with solutions that are not valid. So we want to be aware of those and make sure we check our solutions. X's in the denominators can often lead to extraneous solutions, so we want to be careful when we do this. We can approach it the same way we did the first example, by multiplying by the common denominator. the common denominator between 2x and 1 would have to be 2x. So when I multiply this to each term, I've got 2x times 7, which is 14, and 2x times 3, so that's 6x over x. And 2x times 3 again, so this is 6x over 1, or just 6x. So now I'll simplify 7x plus the x's cancel here, so 6 equals 6x. And now I'll get the x's on the same side by subtracting 7x. So 6 equals negative x, or negative 6 equals and again, I want to check for extraneous solutions, so I'm going to plug x back in to make sure that it works. Now I can often do this mentally in my head. So this is 7 over 2 plus negative a half equals 3. When you're adding fractions, you only add the numerators. 6 equals 3. Positive 6 over 2 equals 3. So 3 equals 3. Since that created a true statement, this is a valid solution. And write this one down, and we'll go over it in class.